and we'll go to the other equation of state. I want to look at some of the other class, like second class equation of state, which is known as, one of the equation is called as Beatty-Bridgman equation of state. Beatty-Bridgman US. This may be regarded as second class equation of state, and this is the empirical equation of state. Empirical EOS for gases up to a pressure 25 megapascal. Up to a pressure 25 megapascal. The expression is PV square equals to RT into 1 minus CY VT cube V plus V0 minus VB0 by V minus A0 into 1 minus A by V. You can see it's not a cubic equation at all. Okay? And A0, B0, A, B, C, they are all constants. For different species, they have different constants. So this is one set. Another set, which is very famous, BWR equation of state, which is Benedict-Webb-Rubin equation of state. Benedict-Webb-Rubin equation of state. This equation is a highly unstable equation or highly sensitive. If you slightly part of the parameter, it will leave some wrong results maybe. So you have to be very careful with materials because it is a 8 parameter model. So it's an 8 parameter. Number of parameter more means is a problem because you cannot do much generalization for the 8 parameter model, which is P equals to RT by V plus 1 by V square RT V0 plus V by V minus A0 plus A by V minus A alpha by V to the power 4 minus 1 by T square C0 minus C by V 1 plus gamma by V square e to the power minus gamma by V square. You can see so many parameters, B0, B, A, alpha, all those things. So you have so many parameters. So this also belongs to the second class equation of state. So combining that, it is possible to express this equation of state in terms of compressibility factor. Right? We have seen compressibility factor model for the first class equation of state. We have done it. P equals to RT by V plus 1 by V square into RT V0 plus small v by V minus first bracket A0 plus A by V minus A alpha by V to the power 4, then minus 1 by T square C0 minus C by V into 1 plus gamma by V square into e to the power minus gamma by V square. This curly bracket closed, this first bracket closed. So these equations, this second class, so what we have done, the first class equation of state as a cubic equation of state, what we have, and those equation of state, it is possible to have compressibility factor chart. It is possible to have compressibility factor chart. And the same thing in the compressibility factor chart you can actually look into for this second class equation of state, and those forms are called as virial equation of state. These forms are called as virial equation of state, virial EOS, which is Z, we define as PV by RT, which is 1 plus V by V plus C by V square plus D by V cube, and see equation number 8. So based on this Benedict-Webb-Rubin equation of state, by looking at it is possible to have Z in a, because you know that if you have the compressibility factor then you can write in terms of reduced state. Then also for second class equation of state, we can have material invariant form. We can have material invariant. Material invariant form is so beautiful. It will be applicable to any material. That your one graph sufficient. Any material you can apply. Excellent idea. So same thing you can apply for the other equation of state. So you just see that for and this will be all approximation. First class equation of state, the beauty is you don't do any approximation. Here we will see how the approximations will be. So next, let's proceed. So this equation of state in terms of pressure, we have Z equals to PV by RT 1 plus B prime P plus C prime P square plus D prime P cube. Equation number B. And how to calculate the B prime, C prime, D prime? Can you correlate with B, C and all? B prime, C prime, D prime can be correlated with B, C, D. Can you correlate it? Yes. We can replace P by this equation, P by in terms of this formula. That formula is actually given there. With that, you can actually get the V term here. Okay. So P is nothing but ZRT by V, right? So this is also formula in terms of V, right? And in that, we can prove B prime, which is B by RT. Am I correct? Can you tell me C prime? B prime is easy. I can easily write. Can you tell C prime? What is C prime? You have to remember that you have to see the coefficients of the same term kind of terms. Okay. Otherwise, it will be a problem. What will be C prime? Any idea? What will be C prime? C prime? Pardon? Yes, madam. C by R square. That's all. Z square. Z should not be there, no? The function of Z. Z is a function. There is dependent variable. Z independent variable.
There is a C by R square T square.
Check it out whether what something we are missing. C by R square T square not the exact answer. There is something else. It is not the exact answer. Not the exact answer. Because remember that there will be everywhere the Z term will be there. The Z has to be put here, that term, and that factor has to be taken. You have to express in terms of Z. See here, this is Z as a function of B. Here, Z as a function of P. And if you transform it, you get some other function of B. But that is still Z. Z should not be coming here. If Z is coming here, these you cannot compare the terms. You cannot compare the terms.
C by T square.
Pardon?
C by T square.
P should not come. See, what is that? Is that the correct answer? It's not the correct answer. I am sorry. It is not the correct answer. Okay, I will just give you the hints. I won't prove it here. So your B is what? ZRT. Sorry, P is ZRT by B. Am I correct? Yes. So Z equals to 1 plus B prime ZRT by B plus C prime ZRT by B square. I am not saying other terms. We will calculate around 1 plus B prime ZRT by B plus C prime z square r square t square by v square. See, everywhere the z term is there. Everywhere the z term is there. So how to proceed? How to proceed? So here also z is, am I correct? This z term? Yes? Okay. So then how to proceed? Z term is there. You can't help it. Z term is there. How to get rid of this Z term? Okay. So that's your question. That's your home task. So B prime is given C prime, which is C minus B square by RT whole square. I hope you'll be able to prove it. I have given a lot of clues. They are possible end semester, not end semester, second quiz question. So I won't prove it in the class. And D prime is, which is B minus 3BC plus 2BQ by RT whole cube. By RT whole cube. Okay. Okay, I think it will be doable. Please try, go back home and try to do it. So now I want to do this calculation further for low pressure. Let's see what you can get for the low pressure. For the low pressure, what you can get for low pressure, we have Z equals to dV by RT, which is 1 plus B prime P. Remember that for low pressure, if we take to 0, the higher order term will be going to 0. Because 0.1, for example, pressure, value, some atmospheric pressure or something, or 0.01. B square will be what? 0.01 to the whole square. That means 10 to the minus 4. That will be 10 to the minus 6. So whatever. So all will be going to 0 only except that linear term. Okay? And we know that B prime equals to B by RT. So Z equals to 1 plus BP by RT. Okay? And 1 plus B, you can write it down for reduced formula, which is PRTC, RPRTC, which you can write as 1 BPC by RTC, PR by TR. So now you can see one of the simplest real equation for low pressure, the function of PR and TR. So in this also we can actually have that kind of chart, but it will be valid for low pressure, not for the high pressure. Maybe up to, say, PR value maybe up to 1, we can talk about. Beyond, we will take the higher order terms. Okay? But this is the expression, very simplified expression for real equation. Only thing is that to subtract the value of capital B. If I subtract the value of capital B and BPC by RTC is that kind of thing, so that I am going to discuss now. So for non-polar molecules, Z is the function of TR, the function of W also, as I said, which is coming as Pizarro eccentric factor. Is coming as Pizarro eccentric factor, which is also written with the Z0, which is TR plus WZ1 TR. Equation number 8. So you can have some kind of linear relationship of this if you include this Pizarro eccentric factor, linear relationship with this PRT. Because Van der Waals equation of state, only equation of state where W has no role. Otherwise SRK, PR has role. RK doesn't have role, but RK has some other nonlinearity. Okay, so if we have other equations for second class equation of state, so that role has to be counted. Okay, that's the non-polar molecules. So BPC by RTC can be written also as B0 plus WB1. This also can be written as this. So this parameterized, you can just see the parameterized, the entire equation can be expressed as a function of W. This equation is not, you don't know about the function of W, but if you incorporate this and this, what you will get? You get Z from here 1 plus, now B0 plus WB1. If you look at this equation, right? So what you will get? B0 plus WB1. This entire thing is B0 plus WB1 into PR by TR, right? This entire thing is also like this. So this is a function of PR omega or W. This is nothing but Z0 plus W0, right? So this is Z0 PR plus WZ1 PR, which is 1 plus B0 plus WB1 PR by TR. So what are the values of Z0 and Z1? What are the expressions for Z0 and Z1? If you compare the equations, compare both sides. So there will be term or some term will be there which is not having any W. There is some term will be having, so we can actually have the calculations with you. So Z0 is 1 plus
B0
1 plus V0 PR by TR, and then Z1 is B1 PR by TR. Am I correct? And the B0 and B1 they are given for some of the materials, so you can actually take it down for one of the example problems. So it is given as B0 as 0.083 minus 0.422 by TR to the power 1.6, and B1 is 0.139 minus 0.172 divided by TR to the power 4.2. So these are the things obtained from some particular cases. These values of B0 and B1 will be given to you. If it is given, you can calculate Z0 and Z1 as a function of TR, right? For some particular cases. So this is one of the examples. Simplified. See, you can see that real equations are so complicated. It is not like an equation of first order, first class equation of state. They are like second class, and I did only for the low pressure. The high moderate pressure, your equations will be changed because B prime, C prime will be coming. You know the relationship between B prime and B, C, B, D prime, C, B, C, D. It will be really cumbersome to work it out. Generally, people will do computer program and solve it. But second class equation of state for the particular materials, if you have highly non-polar substances, highly polymeric substance, and those kind of cases, when first class equation of state fails, then you can go for Betti-Bridgman or Benedict-Webb-Rubin equation of state. With that, I will finish equation of state. So equation of state is done. So I think with this much of knowledge of equation of state, this equation of state is a big topic. There is still a lot of research going on. People are still working on the equation of state. People are developing equation of state for different kind of materials. There is still a lot of materials in this world where we don't know which equation of state. Even if you employ your regular Peng, Robinson, SRK, whatever, even the second class, third class, you cannot predict the behavior. What kind of behavior? You change the temperature, pressure, you get and pressure, you get the volume, for example. Or if you have the fixed volume and temperature, you get the pressure. You get from the external data. Your equation of state should be the same data, right? It is giving different predictions. That means the equation of state, what you are using is not predicting the physics of the problem. So equation of state is becoming a big topic for research. People still do research of equation of state. And for example, you have a polymeric material, you have another polymeric material, you are mixing it. You got a new composite, new material. You want to have PVT behavior of the new material. Again, the equation of state has become a new topic. So equation of state is a topic of research. It will never die. Although equation of state looks very simple, but if you look at the materials, because material means we don't talk about the ideal gas. Materials means real material. It could be solid state, it could be liquid state, it could be gaseous state. And one equation of state should be able to predict the phase transition as well as the behavior in the liquid phase and the gas phase. Such a beautiful topic, equation of state. Fascinating world of equation of state. One can actually really get into and do the research in the equation of state. So still there's a lot of topic. In fact, these days of nanomaterials, for example, we have the nanocomposite, mixed different kind of nanomaterials, nanofluids, for example. We talk about nanofluid. You want to talk about the nanofluid equation of state? We don't know much. What the equation of state? Big question. One has to do the research and find out. Okay. So we are talking about the thermodynamic properties earlier. If you look back before equation of state, we did a lot of derivatives calculations. We said that we want to have the why we did all sorts of derivatives. If you look back to our notes, you can find out what our objective was to measure the property, to obtain the property like internal energy, enthalpy, entropy at particular temperature and pressure. Because temperature and pressure you can easily measure for any of the rooms, any of the industry, any of the material. Of course, pressure is all the time at atmospheric pressure. On a temperature to measure the thermometer. And with that, is it possible to obtain different other property of thermodynamic property like entropy, internal energy, and other Gibbs energy, Helmholtz energy, so much is there. And for that purpose, in the classes before this equation of state, we have found that we have obtained that this internal energy, the function of, we can write this as T and P, enthalpy also. So you wrote like this, enthalpy we wrote like this, then entropy is also possible to write like this, then A also you have to write like this, you can write like this, and G also you can write like this. Similarly, we can write in TV. If the pressure if you want to have a independent variable, so if you want to fix up the TV, TV is T and V, both are independent variables, it is possible to have internal energy, enthalpy, entropy and other properties in a function of T and V. Right? So these are beautiful parameters. Our temperature and pressure you can measure, and with that we can actually we have calculated these derivatives like rho U, rho T at fixed P, rho U, rho P at fixed T. For example, we calculated rho S, rho P at fixed T, and rho S, rho T at fixed T. Those formulas are known. Sometimes we got some value, some acute formula in terms of Cp, and this what you got at right hand side as a function of properties. What you got as a function of properties? What kind of property you got? For example, rho U by rho S by rho P at fixed T, Cpy. If you have TV plane, rho U by rho T at fixed B, Cv. So you get in terms of thermal properties. Sometimes you get properties in terms of kappa, beta. They are like volumetric expansion coefficient. They are like thermal expansion coefficient. They are like compressibility. If you look at Cp by Cv, it has got some value. It has got some kind of properties. So you get right hand side in terms of property, which you can measure, which is actually tables are available. Okay. For example, when you have Cp and Cv in all the tables, it is actually given in terms of ideal gas. Ideal gas means pressure has to be tending to 0. In moderate pressure, you cannot get Cp. For example, my initial state is T1, P1. I am going to T2, T2. Very simple. I have a glass of water. I am in the ground. My ground temperature and pressure is different. I go to the top of the mountain. The temperature is changed. Pressure also is changed. how my internal energy will be changed, how my entropy will be changed, how my enthalpy will be changed. Okay. So we have to quite often we have to calculate delta U, delta H, delta S, delta A, delta G, and what are they? Which is U P2 P2 minus U P1 P1, H P2 P2 minus H P1 P1, S P2 P2 minus S P1 P1, A P2 P2 minus A P1 P1, and G P2 P2 minus G P1. But this formula is simple, measurement is not that simple. Because measurement would have been simple if your material is ideal gas state. That means pressure is tending to 0 or V tending to infinity. Ideal gas is what? PV equals to RT, which is valid for P tending to 0 or V tending to infinity. Why V tending to infinity? Because PV is a finite quantity. The theory of mathematics says that if you get a finite quantity, if one quantity tending to 0, other quantity has to be infinity to get the finite quantity. And the classic example is Dirac delta function. Have you heard about delta function? What is delta function? Here you say at this point, if it is z, x equals to z, you say delta x minus z dx minus infinity to plus infinity, something like 1, right? Is that, am I correct? Or something roughly like that. What does it mean? I just try to correlate this PV equals to RT with this. This is my area. This is A, this is B. AB equals to constant. It's very simple. A rectangular box. The constant is C. C cannot be changed. That means if I reduce A, B has to be big to make this C fixed. If I put A tending to 0, B has to be tending to infinity to fix this C. And C is what? A finite quantity. That's what P tending to 0, B tending to infinity, and that's what is delta function. So that's the concept. In ideal gas, if P tending to 0, mathematically, V has to be tending to infinity. Okay? Don't put B tending to 0. Then there is a big problem because we have to get PV equals to RT. T cannot be 0. T is absolute scale some temperature. Absolute 0 is not defined. We don't know that absolute 0 is there. It has to be having some quantity, and we know that 273 Kelvin is the thing, and also we can go further down. But thing is that R is having a value, T is having a value, it's a finite quantity, so V tending to infinity. That's the proper justification of the theory of mathematics. Okay, so a lot of things we are learning from the mathematical perspective. So coming back, this quantity, if you want to measure the difference of these quantities, it is not that trivial. Okay. We'll talk about what we have learned. I will see how these quantities will be evaluated for the ideal gas regime. That means if you are in P tending to 0, any material will behave ideally as P tending to 0, right? If any material will behave ideally as P tending to 0. And if P tending to 0, V tending to infinity, that is also coming from here, and also if you put RT by P is V, P tending to 0, V is coming to infinity. Temperature is fixed. So many ways. So we'll see these changes in the ideal gas regime, and then we'll see that for the real substances, how these changes can be predicted. And you need to know the changes. If you don't know, you cannot predict many of the stuff. Okay, so what we know that all these properties we similarly as U, you can also write as U hat TV H equals to H hat TV, S equals to S hat TV, A equals to A hat TV, and G equals to G hat TV. So either TP or TV plane, you can, but we don't go for TV. You can also go for TV plane, but generally we don't go. Either we go for temperature, pressure, temperature, volume independent properties. PV you can do that, it is a bit cumbersome because temperature is very easy to measure. Either pressure or volume you can measure. That's it. We can have the complete prediction of your well. So as I said, we initially talk about ideal gas regime. If the pressure is tending to zero, how these changes will be, we calculated. Then we go for real substances. So we know ideal gas as Ig. You know ideal gas as Ig. Okay, we know ideal gas as Ig. So PV equals to RT. Ideal gas PV equals to RT. And for this purpose, we have to calculate the kappa, beta, all those things. For that purpose, it is always better to calculate dou P by dou T at fixed V. How much it is? How much for the ideal gas? R by B. R by B and dou V by dou T at fixed P, which is R by P. Am I correct? Now one can calculate beta, one can calculate kappa. So beta is 1 by B dou V by dou T at fixed P. How much it is coming? PV equals to RT. So from that we can get 1 by T, right? Kappa is minus 1 by B dou V by dou P at fixed T. Dou V by dou P at fixed T. From here you can calculate and how much you are getting? How much you are getting kappa? How much you are getting? 1 by P. All of you agreed? 1 by P. Yes. So you got beta and you know what is positive. So beta you got 1 by T and kappa you got 1 by T. Two interesting, two important terms you got. Now we'll be talking about dou U by dou V at fixed T. Please turn your notes, previous classes, see how much you got this expression, dou U by dou V at fixed T. Dou U by dou V at fixed T, how much you got? Dou U by dou V at fixed T. T beta by kappa minus P. T beta by kappa minus P. How much for the ideal gas? Beta is 1 by T. Kappa is 1 by P minus P. So how much it is coming? How much it is coming? How much? Is very simple. How much it is coming? 0. You are right. Similarly, dou U by dou P at fixed T. What is the formula? From your expression, dou U by dou P at fixed T minus beta Vt plus P kappa V. Have you got it? Just look it out. Minus beta Vt plus P kappa V. Am I correct? Calculate. How much you are getting? Dou U by dou P at fixed T. Dou U by dou P at fixed T. You have all the values. Beta, kappa, everything is given. I have done it for the ideal gas. 0. So much interesting results you are getting. And making your life so simple. Okay? So these derivatives, although some complicated terms are there, but ideal gas, they are going to 0. Excellent. Very nice result. In fact, earlier we didn't know that this derivative should be 0 for the ideal gas. Okay? That's why we were talking all the time dou u by dou t at fixed v, not dou u by dou v at fixed t for the ideal gas. Dou u by dou t at fixed p. We never talk about that. We always talk about dou u by dou t at fixed v, which is Cv. What is dou u by dou t at fixed p for ideal gas? The formula is given to you: Cp minus beta VVP. Cp minus beta VVP. How much it is? Cp minus beta VVP. How much it is coming? Pardon? It is so not that complicated. It's very simple. You will get very cute form. Check it out. Your results. Not looking at me, because you can have all the things formula with you. Cv. How many people are agreeing with Cv? Okay, so many. You are right. You will initially Cp minus R, and you already proved for ideal gas Cp minus Cv equals to R, and that's it. Beautiful result. Excellent result. We didn't know earlier. Dou u by dou t at fixed b is Cv, but now we are saying dou u by dou t at fixed p is also Cv for ideal gas. Not for the real system, for ideal gas only. You know that, we already know that dou u by dou t at fixed b equals to also Cv. Now if you look at these four quantities, dou u by dou t at fixed p is Cv, dou u by dou t at fixed b is Cv, but these guys are 0. So what can I conclude? Earlier we knew that Q equals to Q hat Tp. But if I say U Ig, ideal gas, U hat Ig, what will be the function here? What is that? Why? Because if you say duig, dou uig by dou t p dt plus dou uig dou pt dp, and this guy is going to be 0. So this is nothing but, you can write this as this is no more the pressure, this is the temperature, and that's it, and the function of temperature. Similarly, we have uig, which is u hat ig from the TV plane. So this is for the TP aspect, the TV aspect also. In fact, you should be getting the same result. This u is the function of t, is invariant. Which part you are taking, TP part or TV part, is thermodynamic property. Again, it is verified. If you get different results, it's the wrong thing. So you have to check that. What is actually meaning to that? When you calculate these quantities, this is my T1, P1, this is my T2, P2. My thermodynamic path is this and this. So along this path, if I say this is my, generally we say P1, T1, because we always write coordinate. So this is T plane, this is P plane. Am I correct? Yes. Along this line, temperature is constant. So, what are we measuring here? We are measuring along this path delta U or dou U by dou P at T1. Along this path, I am measuring dou U by dou T at T2. That means when you want to measure, you first measure the change with respect to the T1 constant, and if you go to that part, P constant. Okay? So, what it says that for ideal gas, both P1 and P2 are tending to 0, the low pressure limit, very low pressure limit. So, when we talk about the change of pressure, so this part, that will be quite negligible. This change is not negligible. That means, if you go around that, you won't see any change in the property, you will be having a change in the property. But this will not be the case for the ideal system. This will not be the case for real system. Okay? And overall change is what? You know that, which is dou U by dou P P dP plus dou U by dou T P dP. That's why you get a complete change. Okay? And it says that delta U is this, delta P is increment. If this is constant ratio. Otherwise you have to do integration. For enthalpy, what will happen? Internal energy is over. For enthalpy, it can be written as function of Tp, function of Tv. For Hij, what will be the status? Will that be same? Hij. We also have HTP, HTV. You have HTP and HTV. So what I want in the next class, when you come, we just try to find out dou H, dou PP, dou H, dou VT. We know that dou H by dou TP, which is Cp. But what is the value of dou H, dou TV at ideal gas? Once we have ideal gas, you just see whether Hij question mark, H at Ig TV, H at Ig TP. We don't know so far. We can go back home, try to calculate once, because remember that you need to, as a chemical engineer, you have change in property, change in this measurable quantity, temperature, pressure. We need to measure the change in the thermodynamic property, and for that purpose, these fundamental derivatives are so important. Now we can see why we have done so much of fundamental derivatives, because they are required for our chemical engineering perspective. Thanks for your kind attention.